we move to the next presenter, which comes from Nova School of Science and Technology from Lisbon, Portugal. The presenter is Ayman Sabah. Ayman Sabah had his BS degree from Yarmouk University in Jordan. Later, he joined Medipol University, Istanbul, for his master degree. And now he's pursuing a PhD degree, as I told before, in Nova School of Science and Technology. But most important is that Ayman has joined a group on the European Training Network as an early stage researcher, which is quite good. Congratulations, Ayman.
Thank you.
And so this is a project funded by the Horizon 2020 program. So thank you, Ayman, for joining us and for your participation in this contest. Thank you, Ayman. The ground is yours.
Okay. Good morning, everyone. This is Ayman. I'm a PhD student in FCT Nova University. Today, actually, I'm going to present one of our recent works with the title Aggregate Interference Power Characterization for Directional Beamforming Wireless Networks. So I hope you enjoy the presentation. Regarding the outlines of my presentation, first, I will make a brief introduction about 5G requirements and use cases. Then I will talk about directional beamforming technology. I will mention also the importance of characterizing the interference in directional beamforming networks. Next section talks about the system model. After that, I will go through some mathematical steps needed to characterize the aggregate interference. Last sections validate our results through simulation. Then I will conclude. So the advancement in telecommunication was started from the first generation in 1980s with some basic services like analog communication with 2.4 kilobit per second, and reached to the fifth generation 2020 with communication more than 1 gigabit per second with different services. These services have been classified into 5G into three groups, actually. The first group is enhanced mobile broadband communication, where 5G is expected to support more than 10 gigabit per second communication. The second one is called massive machine type communication, like Internet of Things networks, where 5G is supposed to support connectivity with 1 million devices per 1 kilometer square. And the last one is ultra low latency communication, where 5G is supposed to support communication with latency less than 1 millisecond. To cope with 5G requirements and user demands, recently several technologies have been identified in the literature. One of the well-defined technologies is called millimeter wave. Definitely, millimeter wave will provide large bandwidth, which is necessary for high data rate communication or enhanced mobile broadband applications. However, the high frequencies suffered from high attenuation and path loss. On the other hand, beamforming is a technology which has an advantage of compensating or overcoming the attenuation and path loss in millimeter waves. Adopting beamforming in millimeter waves have introduced actually in new interference regimes. This, of course, will constrain the MAC legacy approach, where they designed based on a classical interference models, which entails and motivates interference characterization, which is important for regulating channel access. So regarding the system model we considered in our MOR, we assume that the nodes are distributed according to a homogeneous boson pointer process with density lambda within a circular area with radius r. And also we reference at the receiver at the origin, and we assume that the receiver will receive more than one interference from different transmitters. So the probability density function of having n nodes within the geographical area A is given by this probability mass function. The beamforming model we consider here is a sectorized antenna model, where we assume that the main gain loop is Gmax and the gain of the side loops is Gmin. So since the orientation of the beams is uniformly distributed from minus pi to pi, we can conclude the PDF of the gain as in this equation. Regarding the channel model, we have assumed two types of small scale feeding channels, Rayleigh and Raytian. Also, we assume large scale path loss model. GI small I capital represents the gain of the transmitter. GI capital I small represents the gain of the receiver. And Ri is the distance between an ith transmitter, and the reference receiver at the origin. So the total interference seen at the reference receiver at the origin is given by the summation of each individual interference coming from each transmitter. These are some mathematical steps needed to characterize the aggregate interference power at the reference receiver. So regarding the procedure, we first characterize the interference of an individual interferer given by this equation, Fp of I. After that, we were able to generalize that to include all the interference in the region, which is given by N by using the law of total probability. And using this characteristic equation, we can have the high order moments of the aggregate interference, which yields to approximating the aggregate interference power into a gamma distribution given by this equation, where the shape is K and the scale parameter is theta. We have performed some simulation results to validate our system model. At the left side, if you can see, this simulation is the CDFs of the aggregate interference power when considering a Rayleigh fading channel, while in the right side, it considers a Ricean fading channel. The similarity comparison between the simulated data and theoretical data indicates high accuracy and matching of the proposed approximation, as we can see here in the figures. Also, the results reflect the incremental effects due to the increase in side loop gains. So for example, if we move here from 0.2 to 0.3, where we have more gain in the side loops, we can see an incremental effect in the total power. Also, we can see the beam width values here, the effect of beam width value. So if we move from high beam width to small beam width value, we can see a decrement in the total aggregate power. And this is because the power is radiated in a specific direction. So to conclude, we have characterized the aggregate interference power when considering beamforming, and we assume also that the network that the nodes are distributed according to a homogeneous boson-pointer process. The proposed approach was validated through simulation by considering different channel parameters, which confirms the effectiveness and accuracy of the proposed approximation. So thank you.
Thank you, Ayman. The paper is open for questions. I would like to ask my colleagues to make any question they would like to do it. Pedro,
Sure.
or no questions?
I think I will, Pedro, this time he'll take the first stage, and then I will this time, okay?
Okay, thank you.
A very brief question.
Yes.
Thank you, Ayman, for your presentation. This is, in fact, a very robust theoretical work to characterize the aggregate interference power due to the effect of beamforming. So you developed a model, you tested the model by using simulation techniques, but do you plan to develop a kind of a prototype, I mean a hardware prototype, to prove the concept in practice?
Actually, before the prototyping, there are many aspects we have to consider first. For example, the mobility scenario we didn't consider here because this is a basic model. We have to consider also the effect of noise, shadowing, different things. When we get the results that validating our system more, then we may, consider prototyping.
Okay, thank you very much.
You are welcome.
Okay, thank you, Ayman. Thanks for your presentation.
You are welcome.
Thank you.